What specific problem does the proposed adaptive batch size schedule aim to solve in the context of large batch training of language models? And why is this issue particularly relevant given the current state of deep learning technologies?
The proposed adaptive batch size schedule aims to address the generalization gap that arises in large batch training of language models, where models trained with large batch sizes often exhibit poorer generalization performance compared to those trained with smaller batches. This issue is particularly relevant in the current state of deep learning technologies, as large language models, LLMs, now consist of billions of parameters and require extensive computational resources, making efficient training strategies essential. The adaptive batch size schedules are designed to dynamically adjust batch sizes throughout the training process, allowing for better utilization of GPU memory while maintaining model performance. By starting with smaller batch sizes and progressively increasing them, the method mitigates the negative effects of large batch training, such as higher validation loss and loss spikes, thereby enhancing both training efficiency and generalization. This approach is crucial as it enables the training of larger models on less powerful hardware, which is often the case for academic researchers and end users.
How does the proposed adaptive batch size schedule work? Please illustrate the step-by-step process, including details about the gradient approximation and norm tests utilized in the training loop.
The proposed adaptive batch size schedule operates through a systematic process that adjusts the batch size based on the quality of gradient approximation. Initially, the training loop computes the batch gradient using a subset of data points, and the norm test is employed to evaluate whether this batch gradient approximates the descent direction of the full objective well. Specifically, if the condition derived from the norm test is not satisfied, the batch size is increased for the next iteration. This process is implemented in two settings: the DDP, norm for data parallelism, which computes the mean and variance of gradients across different workers, and the FSDP norm for model parallelism, which efficiently handles sharded parameters. By utilizing these norm tests, the adaptive schedule ensures that batch sizes are dynamically adjusted to optimize training efficiency while maintaining generalization performance, allowing for larger batch sizes in later training stages while starting with smaller ones to mitigate loss spikes.
Can you provide a concrete example of how the adaptive batch size schedule operates in practice during a training session, detailing how the batch size is adjusted based on training dynamics?
In practice, the adaptive batch size schedule operates by monitoring the quality of the gradient approximation during training. For instance, if the approximate norm test condition is not satisfied, indicating that the current batch size is insufficient for a good descent direction, the batch size is increased for the next iteration. This adjustment is based on the mini-batch gradients computed at each worker, which allows for efficient estimation of gradient variance. For example, in the training of Microlama 300M, the proposed DDP norm method starts with smaller batch sizes and progressively increases them, achieving a balance between generalization performance and training efficiency. This dynamic adjustment helps mitigate the generalization gap typically associated with large batch training, as seen in the validation loss results where the adaptive method outperforms constant batch size baselines.
What are the theoretical benefits of employing the adaptive batch size schedules compared to traditional constant batch size methods, particularly in terms of generalization performance and training efficiency?
The theoretical benefits of employing adaptive batch size schedules, as outlined in the paper, include improved generalization performance and enhanced training efficiency compared to traditional constant batch size methods. Specifically, adaptive batch sizes allow for smaller batches during the early stages of training, which helps mitigate the generalization gap often associated with large batch training by converging to flatter minima. This approach enables the model to adaptively increase batch sizes based on the training dynamics, ensuring that the batch size is optimal for the current state of training, thus maintaining effective gradient approximation. Additionally, the proposed schedules are grounded in a convergence guarantee for the Atom optimizer, which complements existing results for other optimizers, thereby providing a theoretically principled framework for training. Overall, these adaptive methods not only stabilize training, but also leverage available computational resources more effectively, leading to a more efficient training process.
How was the effectiveness of the adaptive batch size schedules validated in the experiments? Please describe the experimental setup, including datasets, metrics used for evaluation, and how you compared the proposed method against baseline approaches.
The effectiveness of the adaptive batch size schedules was validated through experiments conducted on various decoder-only autoregressive language models, specifically MicroLlama 300M, TinyLlama 1, 1B, and OpenLlama 3B using the C4 dataset. The experimental setup involved training these models with the proposed adaptive batch size schedules, utilizing PyTorch FSDP for models requiring more than billions of parameters. Evaluation metrics included validation loss, where the proposed method was compared against constant batch size baselines and a stage-wise batch size schedule, which is a common heuristic in pretraining. Results indicated that the adaptive batch size schedules significantly reduced the generalization gap and achieved lower validation losses compared to the baselines, demonstrating improved training efficiency and stability. For instance, in the case of MicroLlama, the proposed method outperformed constant batch sizes in terms of validation loss while using fewer training steps, showcasing its effectiveness in adapting batch sizes dynamically throughout the training process.
What limitations does the proposed method have, particularly in terms of scalability or assumptions made about the training environment? What future research directions do the authors suggest to address these limitations?
The proposed method, while effective, has limitations regarding scalability, particularly in its reliance on the PyTorch fully sharded data parallel (FSDP) framework, which may not fully leverage tensor parallelism for models exceeding 7 billion parameters. Additionally, the method assumes a certain level of hardware capability, as it requires multiple GPUs and may not be feasible for users with limited resources. The authors suggest future research directions that include exploring the integration of a new version of PyTorch FSDP, FSDP2, and tensor parallelism via PyTorch dtensor, which could significantly enhance scalability for training larger models. They also highlight the need to better understand the critical batch sizes in relation to gradient approximation quality, indicating that this area requires further investigation. Overall, addressing these limitations and exploring these future directions could lead to more robust and scalable training strategies for large language models.